have your clickers ready. I want to work through one of the problems from the homework with you. I believe it's number 9. So last time we had this table of specific heats and freezing points. Go ahead and jot it down for aluminum and copper, if you haven't already. And I'm going to ask you a clicker question here. And hopefully this is a variation on one that you had for homework, so hopefully it's not too bodacious. Specific heat of the solid. Every substance is different, and also for a specific substance, its different phases are different. So solid H2O, which we call ice, and liquid H2O, which we drink from a glass or something, they have different specific heats. Specific heat for liquid water is 1.00 calories per gram Kelvin, which means that it takes 1 calorie to raise 1 gram. If you just have 1 gram and you want to raise it by 1 Kelvin, you need 1 calorie. That's the definition of a calorie. But if it's solid H2O, you got 0.5. And you can look up, liquid copper, liquid aluminum, You can even vaporize those, and you may think, well, why do you want to vaporize a metal? Well, your electronics are in part made with vaporized metals. They use it to put a very thin layer of that metal onto like a sheet of silicon so that they can then make all the different circuit elements in a processor. All right, here's your question, number 1 for today. We don't have too many questions today. Copper is easiest to heat up, good, gram for gram, compared to aluminum because. All right, what's the because? Read carefully. Okay, 20 seconds to think it over. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Boy, kind of low attendance today. Yeah, the correct answer is specific heat. But the thing about it is the melting point of a given substance, that tells you how difficult it is, how tightly bound the atoms or molecules are. So for aluminum, that's not quite as tightly bound gram for gram. But here's the other kicker. Copper and aluminum, they're different parts of the periodic table. So they have a different number of protons and neutrons in the nucleus, and therefore, 1 gram of copper is a different number of atoms from 1 gram of aluminum. So all that stuff factors in, and it gets kind of complicated. But if you're trying to think up something about heating, what you want to do is look at specific heat, because that's what it encodes. All right, another concept I want to review with you, and basically, a calorie is a unit of energy, as we mentioned last time. It's not defined in terms of the standard meter, the standard kilogram, and the standard second. It is defined in terms of water, liquid water. like these droplets on the sleeve. So so when I talk, all the stuff that we're normally going to do in chapter 6 is going to be in terms of calories, but we could easily do it in terms of joules if we wanted to. And, guys that work, for instance, at NASA, they have a big spacecraft, re-entering Earth's atmosphere. They're burning off megajoules of energy, so they're not going to bother with calories. But the guys that design the substance, at the factory that they put in the heat shield, they're probably thinking, well, how many calories per gram per Kelvin, because they're working with tiny amounts. But those guys at NASA, they're working with big, my brother's an engineer in Detroit, and he designs mostly combustion systems. And if you have a Jeep Cherokee or a Jeep Grand Cherokee, it's likely that you have a throttle body on that system or an ignition system that he designed that has a patent on. But he's going to be working, when you put a little bit of gasoline into a combustion cylinder to move the piston, you're talking a very small number of grams, maybe not even a gram of gasoline, if it's an efficient engine. So. And just to review, 1 calorie is the amount of energy, to raise 1 gram of liquid water by 1 Kelvin. It's equivalent to 4.184 joules. And we talked about James Prescott Joule Tuesday in terms of that experiment that he had with the paddle wheels inside of a bucket of water, and he was measuring the effect of the kinetic energy of those paddle wheels on the temperature of the water. And so he would connect it to a weight and then let the weight fall down, so many centimeters. Those paddle wheels would spin, and that would be added to the water. And then as soon as the weight hit the floor, the paddle wheels would stop, but the water would still have absorbed all that kinetic energy, and that's how he figured it out, the thermal equivalent of heat, which he is famous for. Another thing I want to emphasize to you is, as I said, calories and joules are both units of work, units of energy. And, you can do all this thermal stuff in either of them. But if you're working with calories, you want to work with grams, usually. All right? And if you're working in joules, on the other hand, you want to work with kilograms. So just keep that in mind. Now, mostly I'm going to be over here on the first pair, calories and grams. But just so you know, sometimes you'll see joules and kilojoules and kilograms, okay, for various specs or problems and stuff. So, so most of us, most of the semester we're doing kilograms for mass, but this thermal stuff we're mainly going to be doing grams and therefore calories. Now I want to check homework 15, number 9, with you, which was, how do you heat up 1 gram or any number of grams of aluminum to a certain temperature? And it was kind of a brain burner, and I know I caught a bunch of you on it, so let's kind of review it. And this is going to lead into the concept of heat, melt, heat, which is a standard problem. All right, here we go. Let's say that we have an ingot of 1 gram of aluminum. Now, the specs for aluminum, as you know from your table that you just jotted down, 0.215 calories per gram Kelvin. So what that means is, Diamond, if you want to heat up a gram of aluminum by 1 Kelvin, you can do it, and all you need is 0.215 calories. It's a little bit easier than water, a little bit harder than copper, and gold's pretty easy to heat up too. Anyway, so let me put this up here to the side. So let's say that you want to take this ingot and heat it up by 1 Kelvin. All right. So that's like over here. You're just in, I did this temperature scale on the right to scale. It's exact. Okay, so you're just kind of inching it up, just, kind of 1 Kelvin, just a smidgen. And visually you can see it there. All right. And so 1 gram needs 0.215 calories to smidgen it up by that amount. Okay? And that's what this specific heat tells you. But the specific heat also allows you to handle, well, what if I want to heat something up by 2 kelvins? Okay, we got it. Here we go. You got your 1 gram, and let's say that you want to heat it up by 2 kelvins. All right, so that's a little bit, all right, so this is also to scale from initial temperature 820, and 820 was one of the values you could have had on your homework last night. Somewhere between 800, I think I had it set between 800 and 920, that the temperature could, for each calculation that you did. Anyway, so 822. Let's bring it up another smidgen. All right? No problema. We got it. Just give me another 0.215. And add it to the initial one, so your total Q is 0.430 calories. If you got 1 gram, if it's aluminum, and if you're going up 2 kelvins. That's it. Hey, you guys, the symbol Q is a traditional symbol to represent heat energy of some kind. All right, and we use capital E for total mechanical energy. You know what we use for potential energy a lot? Capital U. Kinetic energy, you know what we use for that sometimes? Capital T. I have no idea why they use capital T. Maybe because it comes before U in the alphabet. But anyways, Q is what we frequently use for, heat energy. And I'll start using that today. So for 2 kelvins, 1 gram of aluminum, 0.430 total. All right. Now, what if you want to go up a little bit further? How about that? Well, let's try it. 3 Kelvin, let's go up by plus 3 Kelvin. From 820 up to 823. No sweat. This one also is drawn in precisely. Another smidgen up. All right? And as before, just give me another 0.215 calories. And bing, that's my energy budget. That's how much energy I've got to get from the SUN or from the barbecue grill or from whatever your heat source is to heat up this ingot by 3 Kelvin. All right, so hopefully you're starting to see a pattern here. And this is the pattern that you needed for the HW. Now, what happens if you have more than 1 gram, more than 1 ingot? No problema. All right, here we go. There's 2 grams. I got 2 of those ingots. All right. Now let's say that they start at 820. And let's say that we want heated up by 1 Kelvin. All right. Now each gram is going to require. So here's my smidgen. All right, we're smidgening up to 821, but we're doing it with 2 grams now. And each of those grams, they need 0.215. So to get this bigger mass up by 1 Kelvin, I need 0.215 plus another 0.215 for the other ingot. So that adds up to 0.430. All right? Now, and you can just, so let's go up 2 kelvins. All right, let's try this one. All right, 2 grams, 2 ingots, go up 2 Kelvin, and here's my temperature indicator. So we're just smidgening up a little bit. But you can do the same process all the way up to 933, to the melting point of aluminum if you want, which was the homework problem. But anyways, so each gram needs 0.430 calories, because it's going up by 2. So the total is 0.860, right, to be heated up. So 2 grams going up by 2 Kelvin, 0.215 plus 0.215 for the first gram, 0.215 plus 0.215 for the other gram, total 8.60. Now I'm going to ask you this question here. Go ahead and jot it down. How many calories are needed to heat 2 grams of aluminum by delta T equal to 3 kilograms? So there's our topic. Go ahead and hit your refresh key because it's a calculation. And let's go ahead and do it. Calculate the Q. And if you've been taking notes, you should be able to get it sorted out right sharp. Okay. And give me your answer to the nearest something point, something, something, something. All right, and actually let me do the question now. Sorry. Okay, you can now get input. Go hit your refresh button again. And you can start putting numbers in. Okay, I can hear you clicking. La-da-dee, la-dee-dee. Round off properly. Use your decimal point. You guys are doing good, though. And it's a pattern. It's there's nothing. I have no idea what that is. Okay, 30 seconds. Desiree. Oh, she's in the second class. Okay. Yeah, definitely double check with your neighbors and stuff. And if you have a neighbor, if nobody's sitting next to you, you just have to use sheer brain power. "15 seconds. You want a little more time? Hurry up. Move it. 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, we got 97 on the books here. Good. All right, let me close that. And let me just, you know what? Let me show you guys this and I'll grade it as we go. The correct answer is down here. It's 1.290. And whoever, you can see here there's some answers that are false. 1.277, a little bit too much rounding off. And I think 0.645. That's half of what, that's for 1 gram. 0.64. Okay, so that's your rundown on that problem. Here's the calculation. A bunch of you made a mistake on that, so let's just double check the calculation. It's basically, for 2 grams, it's 0.430 calories for every Kelvin that you want to go up. So you just basically multiply 0.430 calories per Kelvin times how many kelvins you want to go up. Okay, so you're going up 3. Here's your calculation. And notice here that in the notation that I'm using here, it's kind of halfway to the general form here, but you can cancel kelvins, top and bottom, which is good, because you want it, Q is supposed to be a number of joules or calories. All right, so we got calories left over. That's all we want. That's good. And now you just got to multiply it, 0.430 times 3, and your answer is 1.290 calories. All right, now let me pause for a question if you want me to. Do you have a question? You just stretching? Okay. All right, let's keep going. Now, I'm going to give you the general calculation method, and then we're going to do heat, melt, heat. All right, so the amount of, if you're cooling or heating, use the same equation, and I'll give you the full equation in a second. But, to get that amount of energy, whether it's positive or negative, first you have to take into account the actual thermal properties of the substance that you're working with. In other words, are you working with aluminum? Are you working with copper? Are you working with gold? Are you working with diamonds? Are you working with graphite? Are you working with H2O? Are you working with ammonia? Are you working with CO2? All those things are substances that we work with. So for this you want, for heating and cooling, the specific heat encodes how easy it is to cool or heat. Cooling by removing energy, heating by adding energy, a specific substance. Right? But you also have to account for how many grams. Now that's going to be a symbol M for mass. And hey, you guys, for us, most of the time, this is going to be mass in grams. All right, as I mentioned before, because we're doing calories in grams most of the time. All right. The other thing that you have to take into account, and this is what we were just working on, how many kelvins are you going up, or how many are you hoping to cool down by? If you're cooling down, you want to use a negative. If you're heating up, you want to use a positive number of kelvins. Cooling down negative. So if you're trying to cool from 820 down to 819, that means delta T is minus 1 Kelvin. And for aluminum, that would mean, for 1 gram of aluminum, that would be negative 0.215 calories. In other words, that's how much you have to remove with your refrigeration unit and exhaust it out the bottom of the fridge or out the back of the fridge. All right? Now, a lot of the stuff that we're going to work on is just basically heating and melting. The heat, melt, heat. But, I could do a melt, freeze, melt, and then you'd be working with negative Qs. You'd have to, take away a certain amount of energy to melt stuff and you could do cool, melt, cool, freeze, cool, to go from hot water to freezing it and then to cool off the ice below the freezing point. But we're mostly going to do heat, melt, heat. Now the other thing you got to make sure of, for using the formula that we're about to write down is you only use it while you're in a specific phase. So, you calculate, the Q as a solid, or you calculate Q as a liquid, or you calculate Q as a gas. All right? Because each phase has a different specific heat, which we've looked at. Solid water, 0.50 calories per gram Kelvin. Liquid water, 1.00 calories per gram Kelvin. So you got to know your boiling points and stuff too. You got to be alert for that. But what, the whole calculation of energy to melt or energy to freeze, to remove for freezing, that's a whole different calculation. But for heating, here's your equation. Here it is. Now look at this. This is the heating up or cooling down equation. Q equals mc delta T. Now m is the mass. That's part B of my outline. C is the specific heat. That's part A of the outline. And delta T is part C, and that's where you come in with a positive or a negative. C is positive, mass is positive, but delta T can be positive or negative depending on if you're heating or cooling. All right? And we've got that. So, this business of the phase change to actually melt ice or freeze ice, remove heat to freeze it, add heat to ice to melt it. You can do that, but it's a different calculation. It's not this formula. In fact, it's a little bit easier. All right? So here's our table, and this is why I put the melting points usually on a table. Okay? Now, what happens when you want to freeze or melt? Go from solid to liquid, or liquid to solid. To melt something requires adding energy, because what you're doing is you're breaking apart the crystalline bonds of H2O ice. All right? So in general, that substance or that work that's done is called the latent heat. The latent heat of melting, or the latent heat of, the fancy term for it is latent heat of fusion. So at the melting point, 273 Kelvin, every calorie that you add, it doesn't heat anything up. It busts stuff up, just like Bruce Lee, busting up a bunch of crooks, okay, busting up a criminal enterprise, all right? And so it's the same thing. So that depends basically on how many crystalline bonds you have, or metallic bonds, or whatever the bonding is. Liquid water has a weak bonding structure, but you have to break it up. But once you do, you have it in a gas state, a vapor, water vapor. And we see that every day when there's rain. Water vapor invisibly rises up into the sky. Well, you can see it on infrared, I guess. It rises up, and then it gets to a certain altitude, it cools off enough, it liquefies again. It heats up the atmosphere, cools itself off, and becomes liquid droplets at, some altitude. All right? So it has latent heat removed. It's cooled. Right? And it goes from gaseous to liquid phase. All right? So this idea of at the melting point or at the vaporization, the boiling point, the amount of energy that you have to add or subtract to change from solid to liquid, to change from liquid to gaseous, that's called the latent heat. All right? Now here's a table from a recent examination. I kind of blew it up a little bit. So it's like exam 3 from, 2016 or something like that. All right? And so you'll have this on the cover page, So you don't have to worry about mesmerizing it, but you do have to know how to use it. And you can see specific heats, column 2, and my substances are column 1, liquid H2O, solid H2O, gold, silver, and aluminum. So I don't have copper on this one. I have gold and silver on this one. But you'll see, and on the exam I might have graphite, or something like that. Because what's cool is if you get some really good brakes, they make high-tech brakes with carbon fiber, and that stuff is got a. And one of the thermal properties of it is that it's got a high melting point, which is good for brakes. I mean, you don't want your brakes to melt, and but it's also a good conductor of heat. So it heats up, but then it lets the heat dissipate into the rest of the car. Anyway, so you might see that. Anyways, here's specific heat. And then over here, this is the latent heat of fusion. So this is L subscript F, latent heat of fusion. And this is how you break down the intermolecular bonds for water. And for water, it's about 80 calories. So every gram of water is a certain number of molecules of H2O. And each pair of molecules has got to be busted up like Bruce Lee and Chuck Norris. All right? And gram for gram, it takes 80 calories. All right? So all you got to do for latent heat of fusion, to this part of the Q equation, just multiply whatever the latent heat table says times how many grams you got. All right? So that's pretty. So if you have 10 grams, 80 times 10. If you have 1 gram, 80 times 1. If you have 17.5, 17.5 times 80. If it's ice or liquid. And this is what you remove if you're going from liquid water to solid water. You've got to remove this with your refrigeration system. And if you're trying to melt, which is what we're going to do in the next clicker question, you've got to add this latent heat of fusion, okay? So, and you can see I've got a bunch of other, 15 calories per gram for gold, 26.5 calories for silver. Aluminum. Whoo! Aluminum's up there. Aluminum requires to refine aluminum and to smelt aluminum, a lot of energy. That's why they have aluminum plants in very specific, right next to big hydroelectric dams, which is why they built, the Tennessee Valley to the TVA back in the Depression. They electrified up the entire southeast, I guess including Florida. Well, we don't have any hydroelectric dams here, but we probably buy energy from up there. But, they got plenty of mountains and reservoirs up there in Tennessee and Kentucky and whatnot. And so they got big aluminum plants up there as well. Also up in the Northwest, the Columbia River, the Bonneville Power Administration up there in the Columbia Plateau. So aluminum's got some interesting thermal properties. Anyways, let's do our standard heat problem. Okay, so what we're going to do is we're going to do a job for Mr. Polar Bear up north. We're going to make a cup of tea. So here's the specs. Classic problem. Heat, melt, heat. You're up there in the North Pole, and most of the time up there near Santa's workshop, it's pretty cold, right? If there's any ice, the ice pack. So your ice is going to be below 273. So in this example, we're saying, all right, my ice is at 268 Kelvin. All right, it's below the freezing point. But I want to make a cup of tea for my friend the polar bear. Let him warm up a little bit. Keep him happy instead of cranky. You don't want to see a cranky polar bear, believe you me. So you want to raise it up to 373, all right? And then you put in your tea bags, and get him a fresh cup of tea. So 400 grams of ice, that's going to give you about a little bit less than a full water bottle worth. So this is a good cup of tea for your buddy the polar bear. All right? And so you want to go, so now look at this. The freezing point of water is 273. So we're starting out below that, 268. And these are just some numbers I made up so I could trot you through this process. So here's what we're going to do. We're going to heat up the ice. It's freshwater ice. And we're going to heat it up from 268 to 273. And for every gram that we've got, it takes a half a calorie. And that's what is that? That's 5 kelvins. Right? And we got 400 grams. So this is going to be a lot of calories to heat it up. But then at 273, nothing happens until we bust up all those crystalline bonds. And then we got some liquid water at 273. And this one's going to be, for every gram, 80 calories. All right? So that's the melt part. Heat, melt, heat. Then we've got, once we've done that, 80 calories for every one of those 400 grams. We've got 400 grams of liquid water, but it's at 273. You want to get it up to the boiling point for a cup of tea, 373. So now you've got a delta T, but it's liquid water. So for every gram, you want 1 calorie. And you got 100 kelvins to go, so you got a whole lot of stuff to put together. All right, so let's get down to it. All right, so here's my calculation example. And you're going to do one in a few minutes for 120 grams. Okay, slightly different calculation. All right, you're going to do a clicker question. All right, so let's go through it nice and easy. Okay, so let's just lay out, just the specs, no particular order, so we'll do latent heat first. This is the Chuck Norris bust-up factor. For melting or freezing, it's 396 kilojoules per kilogram, or 80 calories per gram. And 80 calories per gram, that's what we're going to use. Okay? But you'll sometimes see 396 kilojoules per kilogram. Water needs a lot. It needs to lose that to freeze. It needs to gain that to melt. All right, so up there, everybody's always worried about, the polar ice cap is going to melt, because of global warming and stuff. Boy, that's tough. That's a tough calculation. Do you know what? A couple of years ago here, I think it was back in 2006, that was one of the first winters where they saw by satellite that the exact North Pole, the top of the Earth, the coldest point, right, in the northern hemisphere, didn't have any ice. It was open water during the summer. And so everybody thought, global warming. But you know what it was? It was a chain of weather pattern. It pushed all the ice from one side of the Arctic Ocean and piled it up over by Greenland and stuff like that, and over by Canada. From Siberia over to Canada. But still, you get a lot of melting during the summer up there. It's the land of the midnight sun. And every gram, 80 calories. All right, so now, specific heats. Let's get this jotted down. We're just putting down our specs. And when you're doing homework number 16 tonight, over the weekend, you'll be doing some. And if I give, sometimes I give students a heat melt heat problem with something other than water. Water's the standard. Heat ice, melt it, and then heat liquid water. But I could give you paraffin, wax. When you're making candles, you got to melt it, and then you got to let it cool and solidify. All right. So when you're making candles or anything out of paraffin. So specific heats, let's get them spec'd out here. Okay, solid H2O, ice, 0.50 calorie per gram Kelvin. All right, we got it. And liquid water, 1.00 calorie per gram Kelvin. No problema. All right, so those are the specs, and we're going through a phase transition. We're going through the melting point. We're going from solid to liquid, so that's what we call phase transition. And so we got to do, all these things. We got to heat two different substances, and we got to melt. There are two different forms of the same substance, and then we got to melt it. So our strategy is heat the ice to 273. It starts at 268. Okay? And then we're going to melt all of it, all 400 grams, at 273. So if you have a thermometer in your pot of water, you throw in your 400 grams, and you got a thermometer in there, you're going to see it go from 268, 269, 270, 271, 272, and then 273, and then it's going to hesitate at 273. The burner's going to be on. You're adding heat to it, but at 273, the heat's going to melt stuff. And it won't start going up to 274 until it's all liquid. All right, so that's what happens to water. So this step, 3B, that's where we use the latent heat of fusion, or latent heat of melting for H2O. And then we're going to heat the liquid all the rest of the way up to 373, my final temperature. All right? And now A and C, 3A and 3C, do you have a question over there on the far right? Okay, that's what it looked like, but I just thought maybe you had a question. Okay, so anyways, A and C, we're going to implement the Q equals MC delta T. All right, so that's the easy part. But we got to use a different C, and actually, so here's my two equations, right? For the heating of ice and heating of liquid, water, MC delta T. For freezing and melting, in this case we're melting, just the mass of the water, so 400 grams times L subscript F, that's 80 calories per gram. And we just got to do that, and that's one of those. But we got two different Q equals MC delta T's. All right? So here are my temperatures, my key temperatures. My initial temperature, 273. My phase transition temperature, 273 Kelvin. Excuse me. Initial temperature, 268. Phase transition at 273. And then final temperature, 373. All right? Now, that means I've got two different delta T's for heating. So in my Q equals MC delta T, I've got to execute that equation twice. Once with a delta T of 5 Kelvin, and once with a delta T of 100 Kelvin, much bigger. Right, now, the homework tonight, you might not have as big a pair of delta T's, but you're going to be up in Greenland or something like that for the homework, or maybe Antarctica, the land of happy feet. All right? So you got two different delta T's, and when you're doing heat melt heat, you got to keep it, kind of in your mind separate. I got two different Q equals MC delta T's to calculate. All right, so here's the first one. All right, Q equals MC delta T. 400 grams is M, and that's going to be M all through the way here. We're assuming that we don't lose any grams of water to steam or anything, steam dissipating stuff. That's why we're not going above 373 for this example. And then we've got specific heat, C, 0.50 for solid H2O that we call ice. And then my initial delta T from 268 up 5K to 273. All right, so there's my calculation. Who's got a value for that? Oh, anybody verify that value? Sorry, it's already up there. 1,000. Anybody verify 1,000? Right. Try to verify this stuff. Try to work through it with me, because, it may seem, I'm really going step by step, and I'm blabbing my big mouth a lot on each step so that you can kind of get each concept. But when you're doing it on your homework, it's a lot to keep track of. All right, so let's keep track of the second. And you can do them in any order you want. So we're doing both of the heating equations, Q equals MC delta T. Now this one's still 400 grams, and we're assuming that my chunk of ice hasn't, that my friend the polar bear hasn't snuck in and nabbed a little piece of ice out of the pot. All right, so the same 400 grams is in the pot. But now we've already melted it, and it's liquid, and we're bringing it all, so 1.00 calorie per gram Kelvin for specific heat, and we're bringing it all the way up 100 Kelvin, all the way up to 373, which you can do. You just got to add enough Q. Whatever your heat source is. Propane tanks, you got a propane burner, or sunlight, or whatever, electricity, whatever you got. All right. And you may think, well, Dr. B, this is kind of a hokey example. I'll tell you who has to do this, though. All those guys up at the space station, shuttle, Apollo mission, all those guys in space. If they want to stay alive, they got to be able to do this, because they're going to gain heat from the sun, they're going to lose heat to space, and they got to prepare food, rehydrate food. So it's, they're going to be doing a lot of this, in their planning and stuff. All right, now here's the melting part. Okay, so this is the cinchy one. Just how many grams you got times 80 calories per gram. All right. And I didn't do them in order. The physical order is the first Q, then the third Q, then the second one in this stack here. But, as long as you know what you're doing, you can do them in reverse order if you feel like. As long as you get them all. All right. So you add these up. 1,000 plus 42 plus 40,000 plus 32,000. Ding! 73,000 calories. Okay, and you know what that would be in food calories? 73 food calories. So that's like a third of a Twinkie or something like that. And you know what, guys? That is why when you're up there, you're continually keeping your body at 98.6 Fahrenheit, and it requires calories to do it. Where do they come from? So you're liquid, and you're trying to keep your liquid at 98.6, and if you go down below 90 degrees, you're going to start getting hypothermia. Now here in Florida, the only way that you can get hypothermia is if you're diving in the ocean, or if you're stranded out in the ocean and you don't have a wetsuit. And the wetsuit insulates you. Anybody here do any scuba diving? Okay. Do you have a wetsuit? Okay. And how deep do you ever go? 8 feet? 80? Does it get cold down there? Yeah, I bet it does. And it's a lot of pressure down there too, water pressure. So you're in a scuba suit, and I remember when I was a kid reading the book by Jacques-Yves Cousteau. He was the guy that invented or perfected scuba. And he said that they found out very quickly that they had to replace heat. They would get done with their dive and they'd be shivering. That's hypothermia. And you can get it pretty quickly. Even if you ever pay attention to the TV or the newspapers and stuff, every once in a while there'll be somebody stranded out in the ocean in the water, or clinging to a piece of wreckage from a boat, and they can get hypothermia as well. And that's for water that's like maybe 80 degrees, but it's below body temperature. That's all. It takes longer than when you're 80 feet down. That gets cold down there. But the surface, yeah, you can get hypothermia. And up at the North Pole, forget about it. All right, so here's your calculations. All right, now let's do it on iClickers. Now you're already on numeric, so I want you to work with your neighbors carefully and work out this heat melt heat up in Greenland. All right? But wait a minute. Let me go back here. Let's review this stuff. Do you have a question about any of this stuff that we just did? Question, Angelica.
So how did you split up the 100 Kelvin and the 500? So like
How did I split up 100?
Yeah, how did you get that
The statement of the problem, the yellow rectangle I had, I stated start at 268, finish at 373. All right? Now, your knowledge of the phase transition temperature, 273, then allows you to break that. So 268 to 373 is nice, but you got a phase transition in there. So that means you've got two delta T's. You got a small one, 268 up to 273, and then you got a big one from 273 all the way up to 373. And that's where the 100K comes from. All right? Another question. Okay, let's do it. Okay, and I'm going to give you a good few minutes for this, so just work carefully. And kibitz with your neighbors, interact. In other words, talk. If your neighbor is a human being, if your neighbor is a robot, then just kind of, Here it is. Different mass, 120 grams. Different initial temperature, 260. Different final temperature, 300. So you're not going all the way up to 373, Angelica. But you're going up 40 kelvins, but you got that phase transition in there. All right? So give me the closest whole number of calories. And let me start the problem. And go, just, start working on it. So figure out your delta T's. Get your Q equal MC delta T's figured out. Set them up and calculate. Two people have voted and they're both incorrect. Don't forget, you have to add up everything. You got 3 calculations and the final answer is what I want. The sum of those 3 calculations. Tiffany? What? Latent, excuse me. If I don't have a snack, At the end of this class, I get cranky in the second class. So, Tiffany, you asked me if it's still 80 calories per gram for the latent heat. And the answer to that is yes, because we're still working with water. Now, if you're on another planet and the animals on that other planet live off ammonia, then you got different latent heats there. But go ahead.
Is latent heat the same when changing it from liquid to gas?
Nope.
So if 80 is only for changing.
That's it. Hold on. From liquid to gas, from gas to liquid, that's the latent heat of vaporization. And that's completely different. You know, I think it's like 1360 for water. And then here's the weird part for steam. Steam is a gas. It's compressible. And so the specific heat of steam depends on the pressure. It's real tough. But I think it's like 1363 latent heat of vaporization. Did you have a question? What is your name? What is your name? Amaya? You didn't have a question, Amaya? Okay. Okay. So now I can continue my snack. Is that a Dallas Cowboys hat? Oh. What? Oh, well, you're saying that the Dallas Loser Boys are a football team? They pretend to be a football team. They get paid to. They're actors. It's like a Hollywood production. You know, lots of drama down there. The Packers and the Giants, the mortal enemies of Dallas. Yeah, they suck this year. The Giants are eternal bums. They get a little reprieve every few years, and then they kill everybody. But most of the time, they're bums. Yeah, Barkley's pretty good. I don't know about these guys wearing Dallas Cowboy hats in my presence. No. Would you mind turning that around? No, I don't want you to make the. I don't want you to make the rest of the class barf. I'll endure it. You know. All right, let's see what you guys got here. Add carefully. You know what you should be doing? Double check your numbers and write them down in your notebook. Because I see some people that have added, but they blooped up their adding. You guys are doing good, though. Dallas Cowboys. That's almost like wearing a Florida State Seminoles hat. in here. Or even worse, the Florida Gators. Oh my goodness. No, we don't do any. No, X. No Florida Gator. Axel, I want you to get that guy back there and body slam him. As soon as class is over, he's over the ropes. Yeah, but are you sure you're right? Yo, in the back, are you sure you're right? All right. All right. We'll see. And there's a lot of good answers on the scoreboard here. Okay, 1 minute. $13.5, 17.01, 318. That's a Florida hat. This is bad. Cowboys in the front and you have Florida in the back. Oh my goodness. Traitors everywhere. See, now we got UCF hats up in the front. That's good. As it should. The nerves of some of these students, I don't know. Actually, though, there are times when I actually do root for the Cowboys. You know when? When they're playing the Cheatriots in the Super Bowl. Of course, that never happens. But I mean, if they were, if by some miracle they won a playoff game and then a few more, beat the Lions. Oh, well, that's a lot to brag about. The Lions, the famous 0-16. Did you see the guy he had the Lions jersey and the name on the back was Owen, O-W-E-N, and the number was 16. Never brag about beating the Lions unless you're talking about 50 years ago when they were tough. I don't know. Detroit Lions, the Cowboys have fallen on hard times if they're bragging about beating the Lions. Oh my goodness. Oh, all right. 15 seconds to get your numbers in. Starting right now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We got it? All right, here we go. Raise your hand if you typed in 13,620. All right, good. All right, now, I want to show you, let's take a look at some of the answers. Now, those of you, 13,080, you forgot something. 12,000, that's, I don't know what that is. So here's 13,620. And here's 13,200. I don't know what you did. You rounded off or something wrong. 13,080 is just a few people. And these ones are possibly, you added some number in twice. And frequently I can figure out these errors. But anyways, this is the correct answer. Let's go back to the YouTube. All right, now, your homework 16 is going to be heat, melt, heat, plus a few more thermal concepts, because our next topic is calculating thermal equilibrium, which, believe it or not, is related to Q equals MC delta T. All right, you're dismissed early. I'll see you on Tuesday next.